So we move on to the next topic, that is function. Dirac Delta or unit impulse function. Suggest something. An impulsive force. An impulsive force. Let us look at the definition. Now, the Dirac Delta function, this is the Dirac Delta. The Dirac Delta function is given as 0 if x is not equal to 0 and infinity if x is equal to 0. The importance of the Dirac Delta function is that in certain differential equations, example, the one with the constant term is where f of t, the certain differential equation, the f of t where f of t is a function where f of t represents functions, where f of t represents functions thus have heavy force applied to them, but for a very short time. A very short time. We learned previously that the unit step, the f of t is piecewise continuous, pieces of functions that are continuous, or they can even be a discontinuous function. Now, but for Dirac Delta, there could be a situation where f of t represents forces that are applied on objects for a very short time, heavy force, a heavy blow for that is applied on an object for a very short time. An example is considering a situation like you are in a carpenter shop. Now, the carpenter has a nail on a wood and is going to apply a heavy force like a hammer on the wood. The hammer, it comes with a heavy force. It hits the nail, but for a very short time. So you have pow. Okay, it's just a short time. Pow. Pow. No reasonable carpenter will do this pow and will be leaving the hammer on the nail. No, it is a heavy force on the so it can be pow, 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 pow. Heavy force hitting the nail suddenly for a very short time. Okay, that is impulsive. That is an example of such a situation. Okay. So we need to know certain properties of the Dirac Delta functions. We have properties. The first one is the first property that we will consider, the first and possibly only property you will consider is this. Now look at this carefully. We'll consider this. This is more specific, this is more general. Anytime you are integrating a Dirac Delta function, We are integrating a Dirac Delta function, but there is something at the back of the Dirac Delta function. There's a function of t at the back of the Dirac Delta function. Okay, how would you get this answer? Now, first of all, the Dirac Delta function, this one, equates it to 0. So that is the first equated to 0. Make t the subject to get a. Now, because this answer a, it falls between this, from negative infinity to positive infinity, certainly a is between them. So that tells you that it is possible to find an answer. And this a that you have gotten, go and put it inside the function at the back. So when you put a inside t is equal to a, you get f of a, and that is the answer. Now, if you have a situation like this, let's say 0 to positive infinity, f of t, Dirac of t minus plus a. Okay, you asked dt, sorry, yeah, dt. I should have had a dt here. If you ask to solve this, the first thing to do here is t plus a is equal to 0. T is equal to minus e. But minus a is not between this and that. Is it true? Minus a is not between 0 and infinity, assuming a is positive. So that tells us that this answer is impossible. This question is impossible, or has an answer of impossible. This question has solution that is impossible. So these are the properties, the basic properties of the Dirac Delta with respect to integration. We'll learn how to take a Laplace transform of the Dirac Delta. So first of all, let's solve some integration problem.